So before I start, I'll again start in my usual way. Do you have any questions? From what I understand, we have our exam today, right? It's in the afternoon, and could some of you explain where the exam is going to be held and so on? Is it in the same tutorial location, Shivam?
So the exam will be at the same place where we were having the tutorials, as here. For example, 3 to 4, then we'll have a break. After break, we'll go to the hydraulics lab, see the column experiments.
Hi. So, so it's a 1-hour exam, and we'll be tested on some of the concepts that you have learned. So what I was proposing to do was, we have 2 1-hour sessions in the morning. So the first one we will try and do it as usual. The second one, I've sort of deliberately kept it a little short, so I might be done in half an hour or so. And I also want then that to be an opportunity for you to ask me any questions that you may have. I'll be here till however long I need to be. But if we do get done earlier, if you don't have any questions, then you are free to go and prepare or study or whatever you want to do. But I will be here and be willing to answer any questions that you may have. Okay. So what we have been covering so far, remember, we have defined primarily 2 kinds of moments. One are temporal moments, and our definition for temporal moments are essentially we are thinking in terms of an experiment that starts at some time t equals 0, and then at some distance along the column we are collecting concentrations as a function of time and then trying to find moments. And we have been linking them to our idea of moments from probability distributions. The first moment is essentially the mean. The second moment, or the second central moment as it's called, is the variance, which says something about the spread around the mean and so on. And we have been doing the same thing with the concentrations too. If I have flux concentrations, and as you did in your tutorial yesterday, if you divide it by an appropriate normalization constant, it has the same properties of a probability density function, and therefore I can talk about its mean and standard deviation and so on. Okay. And we basically try to leverage then some of the advantages we have. So we have talked about temporal moments, and the definitions that we have been using would suggest that this is t to the power of n dt. Okay. So when we do temporal moments, we are typically thinking in terms of flux concentrations, but this gives us essentially our definition for temporal moments. So that means at some location in the column we are observing what is happening in time. Okay, but we are fixing the location. The other kinds of moments, which we have called as spatial moments, are essentially we fix time and try to see where the solute is at various locations in the column, and essentially try to invoke the idea of travel distances as a random variable. And so our spatial moments, we have essentially defined them as perhaps either 0 to infinity if it's a semi-infinite column, in which case we have called them as depth moments, or minus to plus infinity if it's an infinite column. Okay. In this case, notice that we have done it in terms of x, and the concentrations that we have then dealt with are typically either bulk concentrations or resident concentrations. But this has been our definition for spatial moments. Okay? And we have tried to interpret them in terms of travel distances as a random variable, and each of them, c sub f, if I divide it by a normalization constant, behaves like a probability distribution function. So does this. And therefore our interpretation of moments is also similar to our interpretation of moments, mean, variance, standard deviation, and so on, that we have with random variables. And that connection is fairly important to us. What we also saw was that by using these moments, and depending on the model we are using, advection, dispersion, or what have you, we are able to use method of moments to estimate parameters of our model, which is also something that you did in your in your tutorial yesterday. Okay, you were given concentration data as a function of time. You converted that to a probability distribution function. If it's the advection dispersion equation, you found the velocity and dispersion, alpha and beta if it's a gamma distribution, mu sub y, sigma y square if it's log normal. Any other thing, you'll be doing the same thing. Moments. We also distinguish specifically between advection dispersion type models and stochastic convective type models. Okay, we said they come from different considerations. But yesterday also in your assignment, we said if we are given a model, what does it take for it to be a stochastic convective model? Okay, what should be the behavior of the parameters so that it can become a stochastic convective model? The reason is stochastic convective models intuitively are very nice. For instance, as we talked about yesterday, if everything else remains the same, if I double the length of my column, I expect the travel times to have doubled. And therefore, the random variable which was describing travel time in my original column, 2 times that should be my random variable describing travel times in my new column. And so that kind of intuitive simplicity also helps us. And what you saw yesterday was that the equation, if you have data which you observe at a certain location first, and then use that, that distribution, assuming it's a stochastic convective model, you can essentially try and predict what the PDF would be at some other location. Or you can simply use the advection dispersion equation itself, because that has the advantage of having L or X as part of the model, and you find that they're both going to be different. So it's a good question to ask. Something that you should think about is, so what should happen to my velocity and dispersion? How should they be changing with length, perhaps, so that the advection dispersion model behaves like a stochastic convective model? And that would be useful to know. In fact, that could be asked of the other 2 models also. How should parameters alpha and beta change so that the gamma distribution is a stochastic convective model? Or how should mu sub y and sigma y square should be changing so that the log normal function that we have is also a stochastic convective model? So all of these are interesting questions for us. What we want to do today is come back to the idea of temporal moments. I want to essentially show something more about temporal moments, show the kinds of analysis that we do, what more you can do with temporal moments. Specifically, I'll introduce the idea of moment indices. Okay? So when you do compute these moments, what else can they be used for to help us with understanding, what is happening within the soil column? We will start with something called the local equilibrium assumption. Okay. So one of the things I was asked to do for all of you was also sort of clarify, in fact for all of us, what we mean by a solute. We assign a label, it's a conservative solute, okay, versus a non-conservative. So conservative solute is, we think that if we send, as in our experiment, if I have an inlet end where I introduce a certain mass, after sufficient time, if I allow enough time, I should be able to recover all that mass at the outlet end, okay, if I am doing a column experiment. Or if my column is very long, I introduce mass at a certain location. After a certain time, if I sample throughout the column, I should be able to recover all of that mass. That is conservative. Okay. And we also talk about reactive versus non-reactive solutes. Okay. So a non-reactive solute is one that does not basically interact with the media at all. It doesn't undergo adsorption. It doesn't undergo all of those processes. Okay. It is essentially moving only by mechanisms of advection, dispersion, or only moving independently. Whereas if it is adsorbing to this with the solid soil phase, where the adsorption is instantaneous, whether it's time dependent, whether it's linear, non-linear, all of those, or if it's undergoing some other processes, then we basically say it's a reactive one. Okay, it's a reactive. So even though we may recover all of it, it is still reacting with the porous media. Okay, so that's a very loose way of distinguishing. So local equilibrium assumption is an assumption which very frequently is called LEA. What it assumes is, as a solute that is moving through the soil it is allowed to react with the solid soil particles. It is allowed to absorb. However, we assume in some sense that this reaction, that this exchange of information that goes between the solute in the liquid phase and the solid attached to the solid phase is very, very fast. What does very fast mean about it? Essentially, as the solute is moving along the soil particle, it's moving slowly enough so that this reaction can be completed. On the other hand, the velocities are very high, then it will move far too fast. It will pass that solid phase, pass that pores and so on, before the reaction is completely done. So there is all, we all talk about various time scales, and I hope to sort of show you some of those. So local equilibrium assumption therefore means this is sort of the governing equation. We'll assume that it is at equilibrium, so that even if it is absorbent to the solute, all we are seeing is an effect of a retardation, which is given by this expression over here. Okay. So if K sub D tells us the relationship between the solid phase concentration and the liquid phase concentration. If it's a perfectly conservative solute with no reactions, that part is 0, and therefore retardation will be 1. Okay. Rho is the bulk density or dry bulk density of the soil. K sub D is called as the distribution coefficient, and we will assume linear for what we are doing. D is dispersion coefficient, pore water velocity. Gamma is a first order degradation constant, and this is something that we haven't explicitly talked about. We think of the solute as something that can undergo decay. It just naturally decays with time. Okay, and there are many examples that towards the end, one of our last lectures will be about solutes that undergo what are called as decay chains. So perhaps the most familiar one to us in hydrology are the nitrogen cycle change. So nitrites to nitrates to free nitrogen, it's a chain, and with time it converts from one to the other. Okay. In this case, we are essentially saying that whatever solute we have, it simply disappears with time at a rate which is given by gamma. Okay. And then we don't recover it. So that actually does create a problem. So whenever we have decay, I'm going to sort of make a blanket statement and say whatever. I generally tend to be not happy with it, because solute mass, when I try to interpret in terms of moments and probability, it means I have removed some of the probability mass, and unless I have some way of accounting for entire probability, it's kind of difficult to talk about distributions and so on. Okay. So there is that. What do we use it for? So local equilibrium assumption is to compare with other situations when local equilibrium does not exist. So what we are frequently interested in is, yeah, there are reactions occurring and so on, but how different are they from the equilibrium case? Are they sufficiently different that we should worry about them? Or the difference is small enough that I really should not have to worry too much. And what I want to say is, even that kind of information we are able to get from moments. So the local equilibrium assumption essentially says, if I were to use this equation, that would be my local equilibrium assumption equation. Our more general equation would have perhaps many other things. So let me visit or revisit the physical non-equilibrium. Okay. Physical non-equilibrium model was a model that had lots of things going on. Remember, it said that the water region is comprised of two compartments, a mobile water region and an immobile water region. Okay. So basically the porous media has two kinds of porosities, if you will. And typically this is very true for aggregated porous media. So the soil is not like a clean sandy soil, it's mixed with clay, and clay tends to clump together. So in between these aggregates or clumps, there is a porosity through which water can move, but within these aggregates there is a substantial amount of porosity, but the pores tend to be so fine that water doesn't get a chance to move much. So that kind of porosity we will call as immobile water. The solute concentrations that are associated with the mobile and immobile waters have the same symbols. The soil that is attached to the mobile region, that means where solid phase interactions occur, we essentially that portion of the soil, the solid phase concentration is S sub m. S sub Im is the solid phase concentration which is reacting with the immobile water. Okay, and we think that F and 1 minus F are the fractions of the soil that are interacting, say, with the mobile water versus immobile water. Okay. Then we say that the mobile and the dynamic region of the soil, theta sub m and S sub m, Here we have equilibrium reaction in the solid and liquid phase. Similarly, we have equilibrium reactions here with the immobile region between the solid and liquid phase. So K, so the moment CIMR changes, SIM also changes according to a fixed relationship over here. Similarly, if the liquid phase concentration changes either in the mobile or immobile region, the solid phase concentration will change. However, exchange between solute in the mobile region and the immobile region, it has to diffuse through either into the mobile part or out of the mobile part. That is rate limited. So alpha says something about how fast this occurs. Okay, and typically we have this equation then, which says that the rate at which the resident concentration is going to change, whether it's in the liquid phase or the solid phase, is going to be proportional to this difference between the concentrations, and that rate is alpha then. Okay, so this was our model. What we have now added is we are saying that within the mobile region or the immobile region, the solute is allowed to degrade. It's allowed to decay. Okay, and the decay rates, in principle, we can choose them to be different. So gamma liquid mobile, gamma liquid immobile. Gamma solid mobile is a solid phase concentration, what is its rate of decay, versus gamma SIM to indicate decay rate for solute in the solid phase, which is attached to the immobile region. So we could have all of these. Okay. So now with all of this, what is going to change? We will essentially again have a similar definitions for the total solute flux that we had before. We will have a similar definition for what is the bulk concentration, and we go ahead and we can substitute all of these. We will get two equations because we have essentially two unknowns, CMR and CIMR, and so we have these two equations. The only difference now that we have added is because of decay, we have the extra decay terms, okay, the gamma terms. So in the continuity equation, now it's not simply that the change in bulk concentration is matched by how fast flux is coming and going. We are also accounting for the fact that some of the solute is because of decay. Okay. So this is our setting for the P&E model, and this is a more general kind of model, so we will keep it. The other one, remember, was the chemical equilibrium model, and the chemical non-equilibrium model had a different conceptualization. There was only one water compartment, mobile. However, the solid phases which is attached to this mobile water, at some places this exchange between the solid phase and the liquid phase occurs instantaneously at equilibrium. Okay. And there are other sites, type 2 sites, where this exchange is rate limited. That means it depends on this rate alpha. Okay. And therefore, the exchange between the solid phase concentration and the liquid concentration C is proportional to alpha. It's also proportional to the solute concentration difference between the liquid and the solid phase concentrations. Otherwise, our usual definitions will apply for solute flux, therefore flux concentration, bulk concentration. We substitute all of these. We are going to get into two equations again. C is one, the concentration in the mobile region is one unknown. The other one is essentially the concentration in the solid phase, two equations. And we talked about how we can do Laplace transforms and try to get at the moments and so on. Okay, so this is just revisiting those two. So in this context then, what we do, and I think this was something that Professor Srivastava also talked about earlier in his lecture, we use non-dimensionalization because we have now so many parameters. Okay, so for this chemical non-equilibrium model and for the physical non-equilibrium model, we have a whole host of dimensionless parameters. T is time, which is non-dimensionalized with respect to the actual time, and L over V. So length of the column divided with velocity will give you another time. Z, the distance, is simply scaled as x over L. Okay, so these are just independent variables. What we also do is non-dimensionalize the concentrations. So basically, if the inlet concentration is at C0, we say we'll non-dimensionalize the concentrations with respect to C sub 0 for both the models. So C1 and C2, C1 would be the liquid phase concentration, C2 would be like the let's say the solid phase concentration, but they are going to be both non-dimensionalized. So in the chemical non-equilibrium model, remember we have concentration in the liquid phase, concentration in the solid phase. For the physical non-equilibrium model, these are essentially concentrations in the mobile and immobile region. Okay, so different non-dimensionalizations. Then gamma 1 and gamma 2 are essentially decay rates, okay, and these are also non-dimensionalized. We have 4 non-dimensional parameters. One is the retardation coefficient. One is the Peclet number, VL over D. Beta essentially expresses the fraction of sites that are the fraction of water that is in the mobile region and whatever is happening in the mobile region with the solid phase versus the total soil. Okay. So if the immobile fraction was 0 for us, this quantity would be 1. Omega essentially is saying whatever the reaction rate is, how fast the solid and liquid phase reacts, L times theta over V. Okay, it's called as a Damkohler number. So these are all dimensionless numbers, and these are decay rates. And one of the things that you will notice that all of these dimensionless numbers, not the retardation rate specifically, but the Peclet number, beta, the Damkohler number, and the 2 degradation rate constants, these are all dimensionless, which means they are expressing ratios of 2 similar things. Okay. And if you look carefully, all of them actually express the ratios of 2 kinds of travel times, or 2 time scales. The Peclet number is actually the ratio of travel time because of dispersion versus travel time because of advection. Okay. If the Peclet number is very high, it's advection dominated. Okay. So dispersion travel time is like negligible compared to how fast advection plays a role. Beta is similarly representing fractions in the soil. Omega is a Damkohler number. It says how fast is the reaction rate between the liquid phase concentrations. So that is how fast, meaning that is a time scale, versus as water is moving across that pore where the reaction sites are available, how long is that water in contact with that site. So it basically tries to express the ratio of those 2 travel times. If alpha is infinity, that means the reaction rate is very, very fast. Okay, assume it's at equilibrium. Okay, so omega values very high imply we are essentially at equilibrium. Gamma 1 and gamma 2, notice that all of these have L over V, which is essentially a time scale. So this is saying how fast is decay occurring versus how fast advective time scales are. So they're all basically ratios of time scales. So if we use these dimensionless definitions, okay, whether I use the CNE model or the PNE model, I essentially get one equation or one system of equations. These are the 2 equations I get in terms of C1 and C2, but the form of this equation is exactly the same for both of them. The definitions of these dimensionless terms for the 2 models are slightly different from each other, but otherwise in dimensionless form they have the same equation. And the governing equations we have written over there. Notice that when we started, I'm not going to be carrying flux concentration or residence concentrations all along, because I'm going to keep adding subscripts. We say we look at the context and decide whether we are talking about resident concentrations or flux concentrations. Okay. But this is essentially then the system. So if I work in non-dimensional variables, whether it's a PNE model or CNE model, either of them will work. All I have to do is do the inverse non-dimensionalization to cut back the original variables, but the solution to this non-dimensional system would be the same. And therefore the moment calculation that I would do with these non-dimensional variables, I have to interpret the non-dimensional variables differently for each of the models. As I said, it also means that based on what I observe as a flux concentration, what I am collecting at the soil column N, I cannot actually distinguish whether within the column I have chemical non-equilibrium or physical non-equilibrium. That's a judgment I have to make separately. If I'm partial to physical non-equilibrium model, I'll use that. If I like chemical non-equilibrium model, I have to use that. But the signal that we observe is not going to be able to tell us which is the correct model. So with this introduction, let me see if you have any questions first. All right. So now what we can do is, with these non-dimensional variables, we can essentially talk about finding the moments of C1 and C2. because they're both functions of time, they're both functions of space. So time now is a non-dimensional time, z is non-dimensional space. Okay. So let me again define moments for us. We have our definitions for moments. Those actually have not changed. So let's say we are doing temporal moments first. We will do spatial moments perhaps a little bit today afternoon, but in the second lecture. We will essentially call mu sub n, what we had as mu sub n over here. It's the same definition, except now we are using dimensionless terms, capital T and capital C. Same definition. We'll call these as absolute moments. So basically, we correct the concentration information, compute that quantity, we'll call that as absolute moment. We use normalized absolute moments, which is whatever the absolute moment is, we divide them all by mu sub 0. Mu sub 0 would be n equals 0, so that would simply be the total area under the curve, the 0th moment. What that does is it normalizes the whole thing, also makes it equivalent to a probability density. We talk about central moments, where we are now going to compute moments not about the origin at t equals 0. So instead of just t, we will have t minus mu1 star. So that means the moment is being computed about the centroid. Okay. And this is going to be valid for n greater than 2. So for n equals 2, if I am computing the moment about the centroid, then that by definition is the variance. Okay. So I don't have to do second moment minus first moment square. By definition, the second central moment is the variance. Okay. And so if m sub n are central moments and mu sub n's are essentially absolute moments, notice that I could expand this, in a binomial series, do this term by term integration, and what I would find is m sub n has this relationship with the mu values. That means as you keep calculating lower order moments, you can calculate the lower order central moments also from the moments directly. Okay. But that is, that's useful to know. But these are the definitions that we will be using. Okay. So we will go back to Arista's famous Arista's method. Yes. So the question is, right. The reason we are using mu1 star is we are normalizing with respect to mu0, but we are still taking moments with respect to t. So we are saying, why do we still have this mu0 over here? Okay, so we are subtracting mu1 star, but this other term t multiplying, that is not being normalized as yet. So you still need a mu0 to normalize them all. So what mu0 simply does is takes these moments and divide them by the 0th moment. Okay. But you do still need this mu0, because even though mu1 star you have taken care of it, the rest of it, t minus this, does not have a normalization as yet. Okay. All right. So we come back and say, well, we have talked about Arista's method. Non-dimensional or not, we are able to take Laplace transforms. So we can define what is the Laplace transform of C1. Capital T is the non-dimensional time variable. We will use this definition, and then we know from Arista's method or from the moment generating function property of the transform that this is my definition for mu sub n. Okay. And therefore, what we can do is we can actually evaluate this quantity just as we did previously. That means we take the Laplace transform of the entire equation, we differentiate it, find the solution, and under the conditions that we have, we get an expression like this, where f hat of s is what we are doing initially, exponential some z times lambda of s. Lambda of s is all this quantity. And what we know is, what I want to do is, with this expression, be able to take derivatives with respect to s and set those to 0 to get the moments. Okay. So that has been our strategy. The only difference is we have non-dimensionalized it, and we are doing it, let's say, for the physical non-equilibrium model. Okay. So if I do that, I can get expressions for moments, and okay. And if I'm patient enough, and if I do the algebra long enough, I can get expressions for moments. And this is what m0, m1, m2, m3 is. I should also say that these expressions are going to be only true if you let z equal to 1. Okay. So you would have to do that. So we get these expressions now. So this is the 0th moment, first moment, second moment, third moment, and so on. What you will notice, and what is the purpose of doing these, is if you have an experiment, or if you are dealing with a solute and a soil matrix where you have all these reactions occurring, we think of M0 very simply as the first moment. And in the very simple case, when it was a conservative solute, no reactions, we thought that would give us the travel time, the first moment. How long does it take on an average to move a certain distance? You look at M0 now. M0 is going to depend on the Peclet number, it's going to depend on omega, it's going to depend on gamma, the reaction, the decay rates, and all of those. So all of these, if they are going to occur together, they are going to determine how fast the centroid is moving, or what your travel time mean is going to be. All of these are going to be affected, or all of these are going to affect our estimate of just the 0th moment. I'm sorry, this is 0th moment. So how much area you are recovering under the curve. Okay. Obviously, you can check for yourself that if the omegas are all 0, if the gammas are 0, there is no decay. If there is no decay, then irrespective of what is happening, we will recover the entire solute. It may take us a long time. So if gammas are 0, we should essentially expect M0 to be equal to 1. Okay. M1 is our first moment. So M1 first moment, if you recall, that is essentially the centroid of our breakthrough curve, gives us an idea of the average travel time that particles are going to take. And if, in the very simple case, would have said, okay, that should be equal to length over the velocity of the column. But now, notice that this first moment is influenced by the Peclet number, by beta, obviously by retardation. The Damkohler number is going to affect it. The decay rates are going to affect it. All of these are going to combine together to affect our estimate of the first moment, and second moment, and third moment, and so on. Okay. So if you were to now say, I have observed this, if I calculate my effective velocity by using my first moment, and say, well, this is my length of the column, this is where the first moment is in my concentration data, so that's my average time. If I use that, that means effective velocity is going to not only be influenced by the actual velocity where the Peclet number is, it's going to be dependent on what fraction of sites where you have mobile water versus total soil. It's obviously going to depend on retardation, it's going to depend on decay rates, it's going to depend on the reaction rates, Damkohler number, all of those. So that's why, several of you have asked, what is this idea of an effective velocity? So our effective velocity is essentially saying, whatever is happening within the soil column, if I thought the advection dispersion equation was the simple advection dispersion equation was my model, what value of V or what value of D would make my advection dispersion equation look good? Okay. So if we have all these happening, we have an actual velocity that we think the fluid is moving at, but effectively for the advection dispersion equation model to work, my velocity expression would be essentially influenced by all that is going on in the column. My dispersion expression would be influenced by all of these as well. Damkohler number, the Peclet number would be there, the decay rates are there, the value of beta, the retardation coefficients, all of those are there in some complex fashion, and hence the advantage of moments. Because with these moments, I'm able to now essentially make or have very useful insights saying, what I think is the effective velocity, all of these processes are influencing it, and I can actually see how they are influencing it. So this, in my mind, is one of the biggest advantage of method of moments. Because if I use maximum likelihood, which in this case would be, using some brute force method to fit the parameters to observations, and you would use some optimization technique to do it, you could do it, but then you would not have this interpretation available to you. All you would get is some best fit parameters, and then that's about it. So this is an advantage of moments, also available because we have Arisa's method that helps us calculate these. Okay, so this is perhaps one of the more important messages for us, is all these moments, starting from the 0th moment, all of these moments are being influenced by all these parameters in some complex fashion. Okay. In fact, there's a lot of algebra involved. We can find expressions for any order moment. They're very complex and they're long. And what this table is essentially showing you is if you have eta C1 C sub n, oh, by the way, in your notes, please make this change. This is supposed to be n plus 1, not n minus 1. Okay. That's a typographical error. So what this says is, this is going, if I define an eta in this fashion, like C1 and C sub n, I'm actually able to get expressions for m sub n in terms of etas and C sub n's. If I have physical non-equilibrium model, PNE, where I have non-equilibrium sorption, I have first order degradation. We can say non-equilibrium, I'll use n, d is for degradation, then my definition for eta, C1 and C2 are going to be this. Okay, there are some things happening with translation. There's supposed to be a vertical line over here, so that each of these are separate columns. If it's not there in your thing, just you should draw a vertical line over here. Okay. So you have it in yours? Okay. So there is something in the translation. Okay, that's fine. So what it also means is if I have equilibrium sorption. Okay, and for equilibrium sorption essentially means what? Omega is tending to infinity. The reaction rates are so fast that omega tends to infinity, then my definitions for eta, C1 and Cn will simplify a lot. There won't be any omegas. If I have non-equilibrium sorption and no degradation, okay, non-equilibrium sorption, no degradation means the omega, the gammas will all disappear, so we'll have different definitions for these quantities. And of course, the simple case, the local equilibrium assumption one. No degradation, sorption is at equilibrium, then my definitions for each of these are much simpler. But we can find these moments. And again, like I said, our advantage then with moments, at least in my mind, is first that I'm able to see how each of these parameters, which effectively represent physical processes, whether it's a retardation, whether it's a reaction rates, whether it's mobile, immobile fractions, how each of these are influencing my estimates of moments, and therefore telling me effectively how fast is the solute moving, effectively what is the dispersion that's being experienced by the solute. Okay. So it does get a little more complicated, but we are able to do this then. So this is again, I just present some results more for completeness. All it says is we were using flux average concentrations. I can relate flux average concentrations to volume average concentrations as well. So which is like the concentration or the bulk concentration. So moments in resident concentration and moments in flux concentrations are relatable, and this is just for your reference then. So now let's talk a little about non-equilibrium indices, an idea that Voloki introduced in 1985. And what he was looking at was, well, we have all these moments that we compute, and as I indicated, and I could do this as we have done over here for the physical non-equilibrium model. And what he wanted to do with his moments was say, under what combinations should I really worry about non-equilibrium? So are there combinations of omega, gamma, and so on, such that I actually can neglect? If I wanted to be able to neglect them, how would I try to quantify it? So I'm interested in moments. So that is what he was trying to do. So he said, well, I'm going to define moment indices. So for which we are using the symbol epsilon. N over here is the order of the moment. So sub-0 means it's the 0th moment, first means I'm looking at the first moment, and so on. The superscript says what is it that we are trying to differentiate from in the equilibrium case. So when D essentially stands for degradation. So if I compute the nth moment when I have non-equilibrium and degradation, subtract it from the nth moment when I have equilibrium and degradation, and divide it by what I get under equilibrium and degradation, then this index is essentially telling me when I do have degradation, how different are the moments for equilibrium versus non-equilibrium, but they are normalized with themselves. So we are trying to sort of relatively assess the effect of non-equilibrium when we have degradation present. Okay? So this is what we would have got with equilibrium and degradation. With non-equilibrium, this is the difference. So this difference divided by equilibrium conditions is an estimate of what role non-equilibrium is playing in the presence of degradation, okay, when I am calculating moments. And then n can be 0, 1, 2, so on. Same for this one. Now we are, instead of degradation, we are looking at capital N non-equilibrium. So again, we do non-equilibrium degradation, subtract it when we have non-equilibrium, divide it only when we have non-equilibrium. So degradation is what we are looking at the effect of N over here. Similarly, equilibrium conditions, what role do they have in the presence of degradation? So degradation does introduce some complications, as I said, in which case we would find the nth moment under equilibrium and degradation, subtract it from the nth moment under equilibrium alone, divided by the nth moment. So this is just an index, but since we are able to compute these, we are able to see what is the departure from non-equilibrium. Okay, and so this method allows us to do this without having to do any simulations, without having to do any experiments, simply because we have expressions for these moments. So once we have this advantage with moments, that we are able to relate it to the physical parameters, then we of course want to study what that means. Okay. So we'll shortly go into the results. I also wanted to talk a little about effective parameters. So effective parameters, we essentially think that our governing equation is just this. Okay. For now, don't worry about this. This is one non-dimensionalized. Effective parameters, we will assume that our effective equation is simply the advection dispersion equation with nothing else happening to it. Okay, nothing else happening. If I do that, then I'll get expressions for V effective and D effective in terms of moments for this equation. So V effective will be L divided by the first moment. D effective will be something else, first moment, second moment, but we will get those. What we will do is we will use those same expressions, but now with moments computed under whatever is going on. So that's how we get those effective parameters. So what we are saying is, we have all these processes occurring, we observe breakthrough curves, we calculate the experimental moments like you did, we will equate it so that we get V effective and D effective from this model. So the long and short of it is, we are saying we observe results, we are asking ourselves, yes, we know all this is happening, what value of V and D will make this model look good? That is my definition of effective parameters. So that's how we are defining it. No, there is no other reason just to be able to say that, because we are able to define it. We are saying this is how we do it. This is how we think about travel time. This is how we think about how the solute is spreading. So we'll use these as our effective parameters, and we can go ahead and do it. And then we'll get expressions for effective velocity, effective dispersion, but we have seen these before as well. The one thing I will say is, when you do have decay, as I said, that does mess things up a little bit. If you do have decay, and you observe your flux concentrations as a function of time, now because there has been decay, the total mass of solute that you will recover is less than what you had initially supplied at the beginning of the experiment. Some of it has gone. So the mass that you recover versus the total that you supply, that ratio is mass recovery fraction, MRF. Okay. So to find what should be the effective decay rate, we assume it's a first order decay, then we think, okay, let's find the mass recovery fraction, which is essentially the mass recovered divided by the total mass. I'll call that ratio as being exponential of minus an effective decay rate constant times the T. Okay. The question is, what should T be? Okay. So I have essentially observed my breakthrough curve. I found the mass, or I recovered the mass that was not, I did not recover the full mass, so I took that ratio. In this breakthrough curve, which is a function of time, what value of T bar should I use over here to get the right effective decay constant? Okay. And that is not easily discernible, because decay does introduce many complications. One of the earlier studies proposed this, and this is an improvement, but is not still, at least in my mind, totally satisfactory. You notice that this, when you do this experiment, you can always take the first moment and say that was the average time. Okay. from your by calculating the first moment of whatever outflow curve you have. However, that time over here is not the correct time to put. Part of it is because if you think about it, when you have these travel times, the centroid is in the middle. There are travel times that have come earlier, travel times that have come later. For solutes that is being recovered later, that has been in the system longer, so they have experienced more decay. So we have essentially skewed the curve also. So we do not account for all of those very well, but this is one expression that was given. Okay. All right. Experimental moments, I won't go again deeply into this except to say that this is the trapezoidal rule. We are simply doing numerical integration of this quantity. You can use either this expression or an inertia method. Yesterday we essentially used this expression when we were doing the area for the 0th, first and second moments. Okay. But any numerical integration thing that you want to use would work fine, but these are experimental moments. And method of moments says I compute experimental moments, I equate those to theoretical moments. The theoretical moments are in terms of d, v or alpha or beta or all model parameters, and then you back calculate the model parameters then. Okay. So very quickly let me share some results, and we will not go into great detail over here. So we looked at 4 cases for different values of p, r, beta and omega, and gamma in both phases we left that as 0.5. Okay. So what we are then able to do is, because we have these expressions for moments, we are able to calculate these moment indices. So this is epsilon n with d. So n equals 0, n equals 1, n equals 2, so 0th moment, first moment, second moment, third moment. And for those 4 parametric cases, what they show, if it remains at 0, that means it has no influence. It has no influence because it's an index. It is measuring departure from equilibrium conditions. Okay. If there is no departure, it can be where it is. But as we go further, or as the degradation rate constant increases, typically this departure from 0, which is this difference, in all the graphs will change. Okay. So if you look at the 0th moment and the first moment, you will see how essentially it is departing from equilibrium. The second and third moment essentially, well, the 0th and first moment for 2 cases, essentially they are almost on top of each other, which means if I am only looking at 0th and first moment, I can actually differentiate amongst the 2 relatively how they are affected by non-equilibrium. But by the time I come to the second and third moments, they spread out a lot more. So those become far more influenced, those higher order moments are far more influenced by how far you are from non-equilibrium. Okay. So these are the kinds of interpretations that we get from moment indices. And so therefore for different parameter combinations, you can study how much are they going to deviate from equilibrium. So that's one use of moments apart from parameter estimation and so on. And basically the others are essentially other kinds of moment indices, same kinds of results, and you can see for each of those different cases what is the effect when you change the value of the Beckley number or change value of beta or we change retardation. What is the role of a non-equilibrium? And finally, this is simply equilibrium versus non-equilibrium, and you can see what is happening. If it's only equilibrium versus non-equilibrium, okay, that means there is no decay rate and so on, then of course all of these curves are essentially going to fall on the same line. So with this, let's see how am I doing with time. 10:19. Okay, I'll stop over here and see if you have any questions. So I guess the main message for us is, we have been calculating moments, and you did that in your tutorial yesterday. What to show is the moments, even the lower order moments, if we have things like non-equilibrium, if we have a physical non-equilibrium, if we have reaction rates, if we have decay, all of these are going to influence each of the moments right from the 0th moment. All of those are going to be influenced. So our effective properties that we calculate, V effective is not simply equal to V. It's being influenced by the reaction rate, it's being influenced by the physical non-equilibrium, it's being influenced by decay. All of that is giving you an effective V, which is quite different from the actual V. Any questions? Yes?
Which moment will give us the good parameter estimation? Is it higher order moment or lower order moment?
Always the lower order moments. Higher order moments are actually, well, not only are they more difficult, but typically it is like, if you want to capture the behavior, you are going to want to capture the important features. The important features are the lower order moments. The 0th moment, that's the most important one. If I'm not recovering all the mass, I don't know what I'm doing the rest of the time. I don't care how well I do with the first, second, third moments if I cannot tell about what I did with the total mass. Okay. So yes, so what we typically would do is if we have 3 parameters in the model, we would essentially use 3 moments. Okay. Because then we would have 3 equations, 3 unknowns, we should be able to solve it. It is not, I'm going to say it's not, I think the connection is a little bit, maybe not be as obvious. It may be possible to show, and maybe I should first use a Fourier series example. When Professor Guha was talking about, Shoumen was talking about Fourier series expansion, and we truncate the Fourier series. We don't use all the infinite series. It can be shown that the first few terms are always the best approximation. You add another term, it will improve it, but the first few terms are always the best approximation. If you are asked, I can use only 5 terms in a Fourier series, approximate my function as well as possible, it should be the first 5 terms. You can prove that mathematically. My feeling is, and again, this is outside this particular discussion, can anybody tell, if I have moments, is there any way to recover the original probability distribution function? This is not topic of this course. I'm just curious.
We need to have nth order model. Maybe it can even only the probability distribution there is some moment.
Yeah, that is true. What we know is that for each probability distribution function, if I can get all of the moments, then they are unique. Okay, all of them. Otherwise, I cannot uniquely define it. If I have only the first 2 moments, the normal, log normal, gamma, everything will, we can get them. I have to have all the infinite moments, but we will not have infinite moments. Maybe not. So one of the methods, or this is from information theory, which says is if I have some constraints on the distribution, I don't know the distribution itself, but I know some constraints on the distribution. The probability density function is least informative. It should only be satisfying constraints, and beyond that it should not be able to tell you much more, and that is done by entropy theory. Okay. And there is a way to say that if I am given the first few moments, I can use entropy theory to construct what the distribution should be, but it will not be the original distribution. All it will be is, given the first few moments, what is the most or the least informative distribution that you can construct. And even there, when you are trying to do that method to characterize the distribution, in that method also you should use if you are going to use only 3 moments, there should be the 3 lowest moments. Okay. Any other questions? So let me ask you a question, because when we talk about this effective velocity, you see the effect of retardation. Everything else that we do, if there is retardation occurring, what is happening? The velocity is slowing down. Effective velocity is slowing down. The solute is being held back in the soil. If you have, and same with the Damkohler number, same with degradation and so on, all of them tend to slow down the velocity. Can you think of any instance where your breakthrough curve centroid actually appears earlier than what the velocity of effective velocity of the fluid is? This may not be immediately obvious. It requires a lot of thought. Any case where your first movement would indicate that the average solute particles are moving faster than your seepage velocity or or pore water velocity. Absorption, desorption will only slow it down. Yes, desorption means first it had to slow down and get stuck with the soil and then come out later. So that will also slow it down. And this is not an immediately obvious thing. I mean, if you don't know it, it's fine. It's not a knock on you because it doesn't happen very often. There are very particular cases. One of them is called anion exclusion, which essentially, or effectively what we are saying is, if you think of the pore as a cylinder, what we have as our pore water velocity is the average velocity. Okay, the average velocity, and if I think of a pore then, an idealized pore, if it's a cylinder, it will have a parabolic distribution from laminar flow theory. At the boundaries, it will have zero slip condition, so it will be zero. Somewhere in the middle, it's high, we get an average value. Some solutes react with the soil in such a way that they are repelled by the soil surface. So as a solute particle comes closer to the soil surface repels it back into the pore solution. So these particles never experience the zero velocity close to the boundaries. They are always in the higher velocity region of the pore, and therefore they come out in front of what you think is your average velocity. So that is one, happens rarely, but that's why chemistry, how the soil particles react with the soil is important to know. Otherwise, we'd all be going, how are velocity or how are particles coming ahead of where I thought they should be. All these theories tell me they should be coming later. And for that, I can say, oh, retardation has happened. But there are instances. The other instances you can have is when you have colloidal particles. But that's almost like a different, not quite a different field, but colloidal particles also can be moving faster than the pore water velocity, and if you have solute which is sticking to these colloidal particles, it will move out faster than what your average pore water velocity would be. Okay. All right. I don't want to hold you because I know you're anxiously waiting for tea. We will stop over here. So remember, we are back at 11 o'clock. I'll try and finish my next lecture really fast, and you'll have time to ask any questions that you want.